Hello, everyone, and welcome to the second day of the SEMLA 2021 seminar, the fourth edition of the Software Engineering for Machine Learning Application Symposium. In this series, we prepared for you a very exciting program that will run through June till July 1st. We have 6 exciting seminars that we are looking forward to meet you through and discuss with you through these talks and seminars. So last day, we started with our first seminar with Professor Ben Schinderman, who told us about human-centered AI. In today's webinar, we're lucky to have with us Nisha Talagala, who will cover the topic of software innovation to enable broad-based literacy. Then in the next seminar, the third one, we will have a talk from IBM Watson, from Vera Liao, about explainable AI, and we will cover this exciting topic. Then we will cover the topic of continuous delivery for machine learning with experts from ThoughtWork. Arif and Daniello will cover some of their recent work in this space. Then after that, we will have Yingdun Dang from the team of Windows Azure, who will share with us about his experience in AIOps and will take us through his journey from research innovation to industrial adoption. And finally, we will cover the topic that is also close to my research area in architecture of ML-enabled systems, with an interesting talk from Grace Lewis from the Software Engineering Institute at Carnegie Mellon. So before we can maybe go to the next slide. Yeah. So before we go through the logistics, or before we go through the introduction, we can go through some of the logistics of today's session. So if you have any questions to the speaker, you can use the Q&A panel on Zoom to type your question. You can also vote on the questions that you want them to be addressed first, and I will make sure to direct them based on the popularity and vote to our speaker at the end. This session will be recorded and streamed simultaneously on YouTube. If you're using Zoom, you can find the link for YouTube on the Zoom link, and you can also find it in the email that's sent to you. So please allow me to introduce today our speaker for this webinar, Dr. Nisha Talagala. Today, Nisha will share with us her experience on how MLOps or machine learning operations can derive the AI commercial success, and how to extend access to AI to a wider audience for broad adoption of AI through both technological innovation and through enabling AI literacy. Dr. Talagala is a pioneer in AI literacy and MLOps, with significant experience in bringing and spreading AI literacy to the public. For example, Nisha is the CEO and founder of AIClub World, that focuses on empowering kids from elementary, middle, and high school to learn AI and realize their passions through creative applications of their learnings. She's also a co-founder of Peril, a company that focuses on MLOps and practices to enable AI adoption in the industry. This company has been acquired by Data Robot. Well, it's hard to sum all Nisha's achievements in a few words. She holds 73 patents in distributed systems and software, and she's a frequent and inspiring speaker in the industry and academic events such as SEMLA today. And she is also a contributing writer to Forbes. So without further ado, I will give the floor for Nisha to tell us more about software innovation to enable broad-based AI literacy. So the floor for you, Nisha.
Thank you very much. I'm going to share my screen. And let me see if I can put this into presentation mode. Hopefully everyone can see it. All right. So thank you, everyone. And so I'm going to be speaking with you today about software innovations and software techniques that enable broad-based AI access and AI literacy. And so to get us kind of started, before we talk about the current state of AI and why this is important and where current AI trends fit into it, I'd like to give a little bit of an analogy from another technology that we're all very familiar with, but maybe we don't know much about the history of. And that is about cars. And so now I don't know a lot about cars, but I can tell you a little bit about what I know about cars. So this is a picture of what was called a type B-type semi-racer, which was probably one of the fastest cars out there in 1909. Now, the interesting thing you want to know about this car is that the driver of this car needed to use something called a choke, which was to adjust the air-fuel mixture. And they had to manually control the timing of when the spark plug met the fuel in the ignition. And this was one of several things that the driver needed to be able to do in order to get the car to run properly. And as you can imagine, unpleasant things happen to the car if you did not get the air-fuel mixture right, or if you did not correctly time when the spark plug actually met the fuel. So there are many things like this that the driver actually had to do in order to get this car to operate correctly. Now, why are we talking about this? We're talking about this because there is a bit of a similarity between what that car looked like in 1909 and what AI looks like right now. So most AI today is in the hands of a data scientist. It's a fairly esoteric and, slightly not understood technology in the broad world, and it needs a caretaker. So one of the things that I found interesting about this analogy is that the driver of a car in 1909 wasn't just the driver, he was the engine's caretaker. And without the driver, the engine simply would not have functioned, much less gone anywhere. So similarly, the data scientist today is the caretaker of the AI. It's their job to understand the internals. It's their job to understand how to tweak, manage, care for the AI. They know what its unique quirks are and things like that. So if you look at this analogy, then you think about where are cars right now, which is something that we all know. Cars now are mainstay. Most humans have either been in one or have one or use one every day. And I think it's fair to say that most of us have no idea how the engine works, and we don't really care either. However, we have been taught sufficiently to help us understand how to operate them safely. There's such a thing as a license, which means you don't just get to drive a car, you have to actually pass a test in order to operate one of these machineries because they are still quite dangerous. But we know where to get a license, we know how to study for one, we know how to buy a car, we know how to drive one, we have some idea of what we're allowed to do and not allowed to do with the car, and we have some concept of how to take care of a car. So the reason I'm bringing this up is because this is the transition that occurred in the land of automated vehicles that took them from being an esoteric technology that only the driver really understood to something that the bulk of humanity uses. And this is important because much like a car, AI may be a subset of computer science, but at the end of the day, it is a subset of computer science that interacts directly with just about every kind of user. So in that sense, it has a mainstream leap that it's actually in the process of making. So if you think about it, I mean, one could argue that car engines are part of mechanical engineering, and then why should anybody who's not a mechanical engineer care about this? We care about it because we have to drive them. Similarly, if you have to interact with a digital assistant, or you've even got any kind of a modern smartphone, you're pretty much already interacting with an AI, whether you want to or not. So I wanted to kind of present this, analogy to try to explain how technologies have gone through iterations of going from esoteric, technical things to mainstream applications, and the kind of broad-based, not just innovations in the car itself, which we'll talk about, but also, the combination of how to make these technologies accessible to the masses. And so what we'll be talking about in this talk today is really the technology side of how to make AI more accessible to the mass population. So now let's talk about the AI world today. So the AI market is growing very rapidly, depending on what assessment you take. The assessments vary quite substantially, but it doesn't really matter because ultimately they're all in the hundreds of billions, if not many hundreds of billions. And so some of the things that are important to recognize about the state of the AI market is that the AI market, and this speaks to MLOps, is in a transition from what I would call esoteric to not necessarily mainstream, but definitely heading in the direction of that. And so MLOps has been a very big part of that, because what happened a couple of years ago was that, there were many AI experiments, but there weren't that many AIs in production. Now, and there's lots of both anecdotal as well as mechanical evidence for this. AI has penetrated practically every industry, and the notion of production AI is now not something that just companies like LinkedIn or Facebook or Google know, but it's something that is starting to be understood by the majority of enterprises, as well as systems that are now being able to be used across both enterprises and small and medium businesses and so forth. So that is the state of the AI market today. So you can kind of see that we are in the midst of this transition between going from an esoteric technology that is only understood by a data scientist to something that needs to be operated on and acted on by a large swath of people in the world. And you can also see this if you look at any of the recent regulations that are coming out right now. So for example, if you do a quick Google search, you'll find that a handful, somewhere between 5 and 15, United States, either states or local governments have banned facial recognition. And this is an example of everyday humans trying to catch up with what is going on with AI. So this brings us to the next, the main topic that I wanted to talk about, which is software innovations for AI literacy. So part of this is, before we get into what it means to become AI literate, and I think opinions will vary on this. I'm just going to give you mine, so as a reference point. Generally speaking, what we've talked about in literacy is the idea of being knowledgeable about something. And so typically you think about it as the ability to read and write, but fundamentally it's about knowing enough about whatever the topic is in order to be able to function in your life or in your job. And so computer literacy is a common term. Financial literacy is a common term of how to figure out how to manage your bills. So similarly, AI literacy is a certain level of awareness about AI. So I generally think about AI literacy as something which is basic knowledge and competence that will enable professionals and individuals across the workforce to be able to interact with AI in a way that's appropriate for their business, in some form that is essentially does not require them to become data scientists, certainly not PhDs in computer science, and does not require them to understand the engine, for lack of a better term. They need to be able to operate the car, but they don't really need to know how the fuel ignition works and things like that. But they do have to understand enough about the context, the strengths and the weaknesses, so that they can do their jobs or run their lives properly while interacting with this technology. So now the question becomes, okay, so this is all great. What can we do in software in order to drive these kinds of capabilities? And so that's what the talk is really about, is how do we create, AI technologies or software technologies around the AI innovations that can help bridge this gap between the average human or the average professional human and the technology itself. So how do we go from the car of 1909 to the car of today? That then obviously is not just the car, there's education around it, but let's talk about the car for a moment. What is it that we have to do in the actual technology in order to facilitate its interaction with humans from all walks of life? And so that's what I'm going to primarily talk about today. And I'm going to talk about some of the technical solutions that we have created in my company that have basically helped us to bridge this gap. And then what we have learned about using these technologies to bridge the gap with actually a fairly wide range of people, kind of everyone from, young people prior to college to doctors, to accountants, to, software engineers who are not data scientists. So we've had a lot of experience with all of these individuals, and I want to talk about the technologies that we've built that, worked in these areas, and also what we learned by actually putting these technologies in front of people. So some of the ideas that we will cover in this talk are end-to-end automation, automation of data preparation and feature engineering in particular, various kinds of code generation and various kinds of app integration and app code generation. So these are the technical, areas that, we've implemented and designed in and experimented with. And I'd like to share some of my, learnings in that regard. So the first thing is to recognize what the AI in business lifecycle looks like. And this is important because, while the data scientists and, very, very deep technical people and the researchers focus very heavily on the algorithmics, most everyday individuals are really focused on the use case in business. And so they see the AI from the point of view of not necessarily its algorithm, but from the point of view of its role in its job function. And so one thing that I think is becoming increasingly clear now, not just to us, but to people in general, is that there is an artificial intelligence has a life cycle. And while the applications vary and the tools absolutely vary very widely, the life cycle itself doesn't vary all that much. It tends to have these stages. You start with a business problem, then you have a notion of data preparation, data gathering, data collection, where you try to identify what data you have that is relevant to your problem. Then you go into essentially a model experimentation and model creation and model prototyping exercise where you select algorithms, you train experimental models and things of that nature. Then once you have a good candidate, then you deploy it, you connect it with whatever is your business use case, and then you iterate. And so the moment you have this, then you have essentially something that can be used by your business. And after that, you have to see whether or not it actually solves the problem and then, continue to improve it. So an example illustration of this could be that, say I wanted to figure out if say I'm a bank and I wanted to figure out if customers were likely to leave my bank. That would be my business need. My data would be likely historical information about past customers, including their various attributes, what they have, whether or not they left. Then I would have some AI models trained. Once I have an AI model that seems to have good experimental success at forecasting who is going to leave and who is not going to leave, then I'm going to connect that in some way with my customer service machinery at the bank, so that customer service people can make an early identification of someone who is at risk of leaving, and then supplement them with some kind of maybe like an offer or reach out to them, figure out what they need in order to be happy and things like that. Then over time, I will assess whether or not my number of people who have left the bank is going down, because if this technique is successful, that is what should happen. And based on possibly more information, more insight into how to make it better, I will iterate, and hopefully with every iteration, things will get better. So that's the overall life cycle. And so when you're interacting with somebody who is not a technical, a data scientist or an AI expert, this is the context in which they want to understand AI. So now the question is, how do you create this life cycle? And how do you do it in a way that's both realistic and also practical? So most likely, you guys know that there are literally hundreds of AI tools out there. And so the lack of tools is absolutely not a problem. The tools are extremely powerful. Some of them are quite easy to use as well. And so, however, they are all unique in the sense that they all represent themselves just enough differently that you do have to have a certain amount of expertise in order to, utilize them. And so to help facilitate learning, one of the things that we discovered was that it was helpful to have an overlay tool that was really entirely about the life cycle. So because the life cycle is generic and the life cycle can be generically understood, if you can help an individual understand how steps in the life cycle convert into specific actions in scikit-learn, in TensorFlow, wherever you do it, then they are able to interact with these tools, but think of them in a life cycle sort of way, rather than Amazon SageMaker does model training with a Docker container sort of way. So the first thing that we experimented with is that we built an overlay lifecycle tool. And I'd like to tell you a little bit about how that actually works. As of today, these are the 4 backend platforms that our overlay lifecycle tool, which we call Navigator, supports. So I'll tell you a little bit about how it works, and then how the commonality across the life cycle is actually sort of manifested in the tool, so that people can see the tool from a life cycle perspective if they're interested, but they can also dig into the details if they're interested. So this is going to be a very busy slide, so I'll go over it fairly slowly. And then the following slides will be equally busy, but will be much easier to understand. So now if we think about the life cycle, so let's look at the bottom part, the white part of this, and show how a life cycle can actually manifest in a scikit-learn environment, running in the serverless Lambda in the cloud, which is one way to implement a life cycle. So you start life with a data set. So this is the data set, as you can see with my mouse. The data set goes through some prep and transform code. That results in a modified process data set. This modified process data set could be trained using a variety of different algorithms. Since we are talking about scikit-learn as the platform, then we would be looking for algorithms from the scikit-learn Python modules. That then results in one or more model artifacts. And then a model artifact will need to be selected, and this iterate cycle could run as many times as you need it to be. Once you have a model artifact, now you have a model, which is a passive entity sitting in somewhere in a storage system that now needs to be served. Now, serving requires that you create some kind of a serving infrastructure for it. Now, one way to create a serving infrastructure inside AWS, which is our context for this, is to create an endpoint and then connect that endpoint through a serverless function to an external API gateway, where then it becomes a microservice that can then be connected to via REST by any application. So this is a simple implementation of an end-to-end lifecycle where you start with the data, you end up with a working app, and then depending on how you want to iterate, you may modify the data, push a new model, retrain, whatever you want to do. And then the app basically gets a new version of the AI as a microservice. So this is an example of an implementation of a lifecycle. And then what the overlay tool does is ultimately it abstracts this lifecycle so that a user can see that first they're in the dataset form of the lifecycle. They will provide the actions that they want to take in that form, and those will get translated into movements inside local storage in AWS. Feature engineering or data prep, they will discuss the actions they want to perform in that function. That will get translated here into dataset prep and transform code that will then be hosted and run. Similarly, the training cycle is something that is abstracted so that the user knows that they're training and that they are optimizing, and then the actual mechanics of executing that will be then translated into the native AWS scikit code. Similarly, the user can say they want to deploy the AI, and that gets translated into specific actions that that take the model artifact, which is an sklearn pickle model at that point, and then puts it into a serving function that then they can connect to with their app. So this is an example of how you can what the life cycle looks like, as well as how you can take the life cycle and see the pieces and then the underlying code blocks, and whether it's a running process, a running Lambda, whether it's an endpoint, whatever it is, it fits into one of these steps of the life cycle. Now, in order to see why the abstraction is actually interesting and important, let's look at this life cycle with a different backend. So this is scikit-learn, classic Python. It is running in a serverless Lambda, okay? Or one or more serverless Lambdas. This is running in one Lambda, this is running in another, and this is running in a third Lambda. So now let's look at this from the point of view of AWS's native backend, which is Sagemaker. So for those who are not familiar with Sagemaker, Sagemaker is an Amazon software product. You can control it via UI or programmatically, and it has built-in algorithms. It also has the ability to bring in custom algorithms as containers. So now scikit-learn is gone. What we have now is AWS SageMaker instead. So you can see that the life cycle, for the most part, hasn't really changed. What has changed is that when you decide to train, you are now training on AWS SageMaker algorithms rather than scikit-learn algorithms. The need to do dataset prep and transform has not really changed. The training has changed. The model artifact has certainly changed, because now what is coming out is a model artifact created by SageMaker, which is a very particular SageMaker model format. That requires a particular type of endpoint, but outside of it, the mechanism is basically the same. The life cycle certainly is exactly the same. It's just that the pieces that get invoked at different stages of the life cycle have now changed. So now let's take a look at this life cycle from the point of view of a third thing, okay, which is the Google Cloud AI platform. Now this is a more significant change. The most significant change here is that this is now running in the Google Cloud, not in the Amazon Cloud. So this is a bug, I will fix it. So now the idea is that you will connect to your Google storage. You will still do dataset prep and transform. But now if you're training algorithms, you're not training AWS algorithms, you're training on the Google AI algorithms. Now, however, the notion of deploying to a microservice endpoint has not really changed. The difference is that a microservice as constructed on the Google Cloud uses a technology called Google Cloud Functions, not Amazon Lambda, but it works in practically the same way at an abstract sense. The mechanics of setting one up is obviously very different. So Google Cloud, then you will create essentially a serverless function there, and you will connect it to an external world for REST. So you can kind of see, hopefully through this, that the overall life cycle hasn't really changed, but clearly the mechanics of shifting these things and executing them in a different backend are clearly very different. So that is one of the things that we discovered, which was that it was really helpful to have this notion of the life cycle abstracted out from the actual tools that did it, so that a user can, particularly a user who's not very technical, who's much more problem oriented as opposed to necessarily AI oriented, can think about the problem in its consequent stages that are essentially, if I were to go up here, they can think about it from the point of view of preparing the data, how many times they want to train the model, the fact that they want to deploy it and the fact that they want to integrate it. And they can even think about improving this. And that thought process is, the same. And then the overlay tool helps them to both, instantiate it in a backend of their choice, as well as if they are, so inclined, they might want to compare backends for the same thing, but still with a very focus on what the problem was rather than what the nuances of Google Cloud Functions versus, Amazon Lambda is. So this is a little bit like driving two cars and comparing them based upon whether you like the car, as opposed to getting into a deep discussion about exactly how the engine ignition works in both cars, which is not your interest anyway. So that's, I think, is the first thing that we discovered, was that you really want to kind of think about the life cycle and help people appreciate the life cycle in a way that uses, real world tools, but are not necessarily hung up on the nuances and the little quirks of them. So some of the things that we discovered we needed to do in this overlay tool to facilitate this, because it sounds great in theory, but then what does it actually take in real life practice to build a tool like this? So the first thing is that you do need to, so all of these training, modules have their own little weird quirks about how they like to think about data. For example, just a random little quirk, Amazon SageMaker does not care for its label column in a supervised data set to be anywhere but the first column. It does not like headers either. So these are the kinds of things that you sort of need to know. And so one of the things that happens in data prep inside Navigator is a removal of rearrangement of the columns and removal of the headers. These are not complicated things, but in order to facilitate the abstraction, you do need to do them. The next thing is that for a human to understand, how to interact with the AI, it's imperative that the AI actually takes inputs in the raw data format and not in the process data format. So I'll give you a simple example. Say that your raw data had a category, and that category was, I don't know, a model of car, whether it was a sedan or an SUV or something like that. By the time you get through feature engineering, you've likely done something like one-hot encoding, and what your AI sees is not a category of sedan and SUV. Your AI probably sees multiple columns with zeros and ones in them. So, and this is all well and good for the training. However, when you're dealing with a user who doesn't really want to know those kinds of things, once the AI is ready and connected to an app, the user wants to be able to enter in SUV or sedan, not whatever it turned into after feature engineering. So this means that whatever you did in data prep has to be automatically generated as inference code in order to make sure that the user is interacting with it the way that they understand the data, which is in its raw, non-processed form. So this is another thing that needed to be done in order to make this viable. The next thing is, clearly, as every algorithm and every engine sees their notion of training and differently, you do need to have a way to abstract out the training parameters and be able to retrieve information about the training parameters in each of the engines. Finally, we found that we needed to create a rules engine to appreciate the algorithm and problem matching, so that if a user is not inclined to, for example, describe that they're dealing with a classification problem versus a regression problem, that by examining the data, we're able to make a recommendation as to what kind of problem this actually is. Because what we found is that when you're dealing with the mass population, you end up with a variety of different skill sets, and some of whom have no interest in this kind of specification, and some who have a great deal of interest. So we created a rules engine that basically helped the user decide if there's an overlay tool and it has multiple backends, which backend is right for them, and what settings for that backend might be right for them. So that basically helps them pick a backend. It also helps them automatically configure the backend in a way that is likely to work for their problem, at least as a first iteration. So these are some of the things that we discovered when we built the Navigator overlay tool. And, some of these we learned by simply actually having to support all 4 of the backends. And some of it was through experimentation and interaction with users and getting user feedback to try to understand what are the things that they wanted to learn about, what are the things that they did not want to learn about. So that, I think, is the first thing that I wanted to cover in my talk, was this notion of the use of an overlay tool and what we needed to do from a software engineering standpoint to create one that actually worked both for multiple backends as well as for users themselves. So that's the first thing. Now, the second thing that I want to talk about is data preparation automation. Now, the state of data prep automation in the commercial world right now is there are a few products out there right now for data prep automation, and people are starting to realize that data prep automation is an important thing. Now, data prep automation fits, covers a bunch of different things, everything from what I would call functional need and what I would call optimization need. So I'll give you an example. A functional need, it will address, things like an AI training algorithm is unable to accept data in any format that is non-numerical. That's a functional need. It doesn't have anything to do with the quality of the AI you get out. You will get no AI out if you don't do that. So similarly, missing values, NAs, any kind of corruption, any kind of format issue, all of these are functionally have to be cleaned up, and data cleaning has to be done for it before the AI at the AI stage of the life cycle will give you any kind of result, good or bad. Once this is done, then there are other things that could materially impact the quality of your AI. Whether or not you normalize the data, you may want to do some feature synthesis to try to find new features that are better than the features that are in your original data. So those things, are not necessarily about function, but they are about good function in terms of optimization. So these are the kinds of things that enable different use cases. And one of the things that we discovered through our learning process was that when you're trying to make AI available to the mass market, there are a lot of use cases out there. And so the more you can do in the land of data prep automation, the more likely that the life cycle is accessible to people with different use cases of interest. So if you, for example, are dealing with a doctor or an accountant, they don't really have a lot of interest in movie recommendations, if you will. Whereas, if you're dealing with someone who's more, marketing oriented, or you're dealing with a student who is really just generally interested in AI, they tend to have a great deal of interest in that topic because it's something that they can relate to. So because of that, what we found was that data preparation automation is really helpful in enabling, novice users to interact, build, and create AIs in areas of their interest, because otherwise, unfortunately, no matter how sophisticated the ML tools are, they just cannot get their data transformed because they don't know enough Python, or they don't understand, the mechanics and why it needs to be done and how it needs to be done. So another area that we focused on fairly heavily was what we call feature engineering or data prep automation. I'll talk a little bit about the approach that we took for that. So the approach that we took for that is that we, approach this the same way that pretty much any kind of, piece of software that has had to do any kind of planning. And you can see similarities in things like query planners in databases, things like that, or for that matter, any kind of, execution code planner. So we built a 3-level, architecture, which we call analysis, planner, and code generator. And so the way this works, and this was written entirely in Python, and this is part of our overlay software's automation in the feature engineering stage. So the way this works is the human provides raw data set, and the raw data set, and the human is also allowed to provide certain insights about what they want to do or what they want to know, or anything that they feel that they would like to use to guide the automatic feature engineering. These two pieces of information are taken into the analysis stage of our automation FE, which does things like basically examines the data. So it will figure out, how many columns there are, how many samples there are, what, the distributions. It will make its own judgment through a rules engine on what some of the columns are. So as an example, if you have a text column, then it will recommend that's a text column. If you have text columns where, only 3 or 4 or just a small number of text entities are repeatedly involved, it will decide that this column is better treated as a category. If you have numerical columns where only a few numbers are repeatedly invoked, even though the type is numerical, it may consider that to be better served as a category. Otherwise, it might consider it to be numerical. It has the ability to recognize dates and times and things of that nature. Then it will also figure out missing values and so forth. Based upon its assessment of the data, it will create essentially a feature engineering execution graph. And that feature engineering execution graph will appreciate these distributions and these types and will create a sequence of transformations that are appropriate to convert this raw data set into something that an AI can actually process. And so this will include, for example, maybe at one stage of the graph, you may have to do a missing value filler. In another stage of the graph, you may have to do a one-hot encoding in order to convert your, categorical columns into suitable numerical multi-columns, or you may have to do some kind of a text vector encoding if you've got a text field and things like that. So all of that is basically uses a rules engine and a combination of heuristics and learning intelligence in order to convert the raw information into essentially what is the sequence of transforms that will need to be done in order to convert this raw data set. Now keep in mind, this is an abstract sequence. And part of the reason why it's an abstract sequence is because of the overlay nature of the tool. Then there's a specific stage that we call the execution stage, where code is actually generated for this graph. And this is reflecting the fact that the graph and the steps that you need to take are logical steps and have really more to do with the data set itself than anything else. And the code is going to be executed in an environment. So for example, if the data set is small, then the code could be well executed in a small serverless function. If the data set is large, then the code may require distributed environment, in which case we generate code for Dask, which is a very popular distributed environment for Python. This is the place where we also recognize that if this is the sequence of transforms required during training, it is also the sequence of transforms required to convert the raw data set into something that the model will understand during inference. And so given that training code is batch optimized and inference code has to be more individual serving optimized, it's two different types of code that gets generated. So this is the architecture that we have chosen, and this enables us to essentially scale out our execution backends so that for the same graph, we can create as many backends as we like as the overlay tool expands to new environments. And as we learn more about human insights, we are able to increase this and then increase the intelligence in this. So that's essentially the engine that we created for the feature engineering automation. And I'll talk in a little bit about the results that we've seen with it. Finally, what we've discovered is that for a certain fraction of learners, it really helps to be able to generate code. So there are, I would say about, I want to say at least 70% of the people that we've shared these platforms with have no interest in seeing the code. But a good about 30% of them absolutely do. They don't have the ability to create the code themselves, but they absolutely have the ability and the interest to read it. So what we found was that this execution pipeline is not just really useful for generating execution code, it's also really useful for generating what we call teach code. And the difference between teach code and execution code is that production grade execution code has to have, lots and lots of error handling. It actually has to interact with the local cloud, and things like that. It should report errors. It has a logging mechanism, all of which is extremely confusing to an average person who just wants to know what this transformation sequence looked like and how they could run it on their laptop. So the execution pipeline also generates what we call teach code, which is a standalone code. It is intended for learning. So it's extremely well documented, extremely clean, but at the same time, it does not have some of the complexities that exist in production grade execution code. So that's the other thing that we do, is that the execution code creates, pipeline creates not just execution code, it also creates standalone teach code. So those are some of the things that and I'll do a little demo in just a minute to show you guys what this actually looks like. Finally, the thing that we discovered was that app integration is one of the most, interesting things for a user, because it's kind of like the conceptual equivalent of you try to teach someone how to use a car, but you insist on only showing them the engine and they never get to sit in an actual car. They're usually not that interested. They may care about the engine a little bit, but mostly they just want to drive the car. So app integration is the AI equivalent of driving the car. So what we discovered for that is that you have to be able to do the deployment and you have to be able to create integrations with different kinds of apps. And so this part that is in red in the life cycle is key to the application integration. Now, we made a choice to do application integration entirely via REST because that supports a large number of what I would call mid-range applications. So if you are in super high performance real-time serving, this will not work for you. But most people who are, for our goal of reaching the masses, this was a very, very generic useful thing, which was to deploy to a microservice endpoint and use REST. So this is generally what our overlay tool has for application integration. It auto-generates an inference pipeline, which we already talked about, which has model inference. The FE inference code is already created by the execution pipeline. This is put in a REST service, a microservice, and a variety of auto-generated web interfaces and code templates are made available to help users explore this AI as they would in an app context. So there's also a series of template apps. These are some of the template apps that are created. And these template apps basically enable you to see and interact with this AI in an app context that is of value to you. So if it is either it's a web page or an iOS app or Android, native Python code, Java, JavaScript, Shell, all of these are template connections that then use the same auto-generated pipeline. So those are some of the 4 areas that we found were actually very helpful in helping a user sort of, who wants to understand the AI, wants to understand the use context, and wants to appreciate sort of how this works, but at the same time, not necessarily get worried in too much of the detail. So I'm going to do like a 3-minute demo of how this works in practice and what this actually looks like to a user. So what we'll do is we will build a small AI to predict the prices of cars. So the first thing is I'm going to load up a data set that's already on the Amazon cloud. So that just makes my life a little easier for the demo. This data set is a standard Kaggle data set. It has about 12,000 samples. And you can see that it has a decent, it's not as complex as a real world data set, but it has a decent number of, features in it. So basically, this is what the data set is. Now, if we go to the feature engineering, and you can see the life cycle basically playing out right to left on the, and how the overlay tool utilizes, and abstracts out the life cycle. So we're going to use the scikit-learn serverless engine with a certain amount of automation, and we want to predict the manufacturer's suggested retail price. So now what is happening is that the that the feature engineering automation code is running its analysis on this data set and is going to make a bunch of decisions about the features in the data set and how to handle them, which ones to convert. It will drop a couple that it doesn't understand, and then it will go ahead and process everything else. So that took about 20 seconds, and you can see that it basically described all the things that it did along the way. So it decided that the problem was a regressor because, because of the label column, did a bunch of formatting, rearranged some of the columns, decided it had a bunch of categorical columns, cleaned up some of them, created test and validation data sets, things like that. So now that the feature engineering is done, then the user knows that logically in the life cycle, they have to go to train. And they can select, a number of training engines, and they can either pick algorithms or automatic. For the sake of the demo, I'm just going to go automatic. So now what's happening is that they are able to execute a train function, which is then being translated in the backend into, in this case, the engine of their choice, which is the scikit-learn engine. And the reason I'm choosing the scikit-learn engine is that mechanically speaking, the Sagemaker engine takes about 20 minutes to execute. And so I don't want to do that in a demo right now. It has nothing to do with this data set. It has to do with the way Sagemaker sets up training jobs. So now what's happening is a bunch of different algorithms have been run, and random forest regressor has been auto-selected and is being deployed as a REST endpoint. So now that it has been deployed, now this is a simple example of an app template. So you can see, so I'll let the app template load up. It's basically an auto-generated web-based app template. And you can see there's a couple of things you can notice about it. One of them is that these are the original raw data features. So this is something that the user can absolutely understand. So whatever these look like when the AI got it is something that unless they want to examine it, they don't need to, because the inference version of the FE code has actually been embedded into this web app directly so that the user can say, okay, I want to select electric cars. And I want to take an electric car that was built in, 2019, and I want the transmission type to be automated manual, okay, and stuff like that. And then tell me what the price of the car is. And you can see that there's explanations as per random forest, feature importance and things like that. So the idea here is that this is an automated web app. And so now the user is interacting with the AI in a way that is contextually interesting for them because they're interested in what it predicts. They're interested in how that changes with features and things like that, but in the terms that they understand, which are the terms of the problem, not necessarily the terms of the AI. Now, if they wanted to do app integration, there's also a whole bunch of, app integration templates that, we found helpful for students. So yeah, there's, so if I look at Python, for example, this is the Python snippet, and this is all auto-generated. So what happens is that, these are all auto-generated templates directly for your AI. So you can see that it's quite literally, this is this particular AI, and this is the code for it. Similarly, if you wanted to see the code that was actually used in order to run the FE, you can go to the train tab, and there's an option here called generate code. And what happens is that it will generate the teach version of the code. Then you can download the teach version of the code. And I'm going to share my screen and show this to you. You can find the teach version of the code. So this is the teach version of the code that was created for this user. So you can basically see that it's Python code because this was Python scikit-learn. That was the engine that they chose. And it's, it's obviously, it's a, reasonably complex data set as far as learning data sets go, but it's not that hard to read. So you can see the actual features in here. You can also see comments that say this particular block of code fill the missing values in categorical features. This particular block of code filled the missing values in continuous features. This code did the one-hot encoding. The model got saved, and things like that. And then there's, if you scroll further down, I think you'll see, okay, this is rearrangement of the columns. There were certain columns it wanted to drop, test train split, things like that. And then here we have, random forest regressor and basically a whole bunch of the learning, functions. So the basic idea is that this is auto-generated through the execution pipeline, and this is the code that was intended for teaching. This is functional code. You can run this locally on the computer and it will do exactly what it's supposed to do. You can run this on the data set and it'll do exactly what it needs to do, and will do exactly the same thing that the production code does. It just doesn't have the production code hardiness attached to it. So those are some of the things that that's kind of how some of these software, creations that we did kind of came together. So I want to just take a minute and talk about what we learned by doing this. So the first thing is that we put this into an AI literacy program that we call the 4 Cs, where the basic idea is that you really want to help people appreciate what AI is, how it works, how to interact with it, without necessarily getting into the details of the math and the computer science, but provide them with a pathway to explore more of the internals if they so wish to. And so we use this, these software technologies in these 2 areas. We wanted to help people of all walks of life build AIs at scale, with real world data sets that they can get from public sources, and also build whatever they like. So it's not that, there are these 3 data sets and this is all you get to build. You should be able to bring in a data set from Kaggle and build things and get a working app, not just a data set. So that's what we used it for. And to date, we've had more than about 3,000 users of this platform, K-12 developers, business users. They've trained more than 55,000 AI models. They've built more than 7,000 end-to-end apps. And they have brought in, to our knowledge, well over 500 custom data sets that were not seen by the platform prior to the, when they brought it in. So this last one, I think, is the one that I'm most sort of interested in that it speaks to the ability of the FE automation to be able to, process and make decent headway with data sets that it hasn't seen before and create end-to-end apps. This, I think, is the second one, which is most interesting, which is that, being able to have app templates has enabled people to build end-to-end apps, which are really useful for people who are not going to be data science experts, but really want to understand how AI apps are likely to work. The other thing that we've discovered that is not in here is you probably noticed that when we did that demo, the whole demo was over in about 3 minutes. We've discovered that for learners of this kind of technique, that iterative cycle is extremely important. Because remember, they are not trying to get a perfect working AI. They're trying to understand how AI works. And the way they understand how it works is by poking it in various ways. What if I do this? What if I do that? And so those kinds of things, the faster the iteration is, the more they learn on their own. And one of the things that I've discovered from this experience is particularly professionals, one thing that they say is, they don't really need to know how to build one because they will not encounter a situation in their professional life where they have to build one. However, what they've discovered is that if they can quickly build one, their level of understanding of how it actually works seems to go up quite dramatically. And that they really do want. So those are some of the things that we've experienced. So I'm hoping that this was helpful. I think I'll take a break now and see if there are any questions.
Okay, well, thank you, Nisha, for this wonderful talk and very insightful talk. We have a few questions, and I also have through your talk, one of the questions that popped up in my mind, that the different users that you have, because you start talking about this analogy between AI and the car example. And when you started giving this analogy, but the users from my perspective were the end user, which is the one that will use the AI without any knowledge about how this AI system were built. So with this particular user, also the question that one of the things that I start thinking of is the relationship between this and the Turing test. For example, do we really need the user, or does the user really does not want to know anything about the system, or they need to be aware of that this is an AI system and have some assumption about how it works? So this is the first part. Then you moved and talked about maybe enabling other type of users. So there was the maybe citizens users, what we call them, those that have business knowledge, but maybe does not know how to really build the application, does not have the technical knowledge to build a fully fledged application, like does not know how to build a really full stack application.
Right.
Yeah. So you're targeting many type of users, right?
Yeah, and one of the reasons why I think we've done that is because I think, this field is so new because, and so the answer to your question, I don't think anyone really knows, how much they need to know, right? So I'll give you an example that might maybe help. So a couple of weeks ago, or maybe a couple of months ago, the American Civil Liberties Union sued the city of Detroit because a facial recognition system misidentified someone as a criminal. And one of the things that was interesting about that was that it was very clear that the facial recognition had made a mistake. But one thing that stood out for me was the police officers involved didn't realize that they were allowed to think it made a mistake. So it's kind of like the police officer was looking at the guy, looking at the picture, could clearly tell they were not the same person, but said, well, the computer says you're the same people, so you must be. So I think that this kind of stuff, so one of the things that we found is that it's really helpful when everyday users are able to see that the AI is not a binary entity. It is not always wrong and it's absolutely not always right. And so when they have some appreciation for the way it works, they're able to put their own judgment ahead of it when they need to. So that's why I think that, it cannot be a black box in the sense, because it's more about making sure that they have the tools needed in order to feel comfortable questioning it. That they need to. So that's why I feel that the, in-depth, one thing that I've noticed is that when people interact with an AI, they really, one of the things I always ask them is, tell me what it got right and what it got wrong. And if it got something wrong, do we know why? And that I find helps people a great deal in just appreciating the middle ground, that it's not a miracle. It's not something that's going to kidnap your kids either. It's just somewhere in between. It's a technology. Does that answer your question, hopefully?
Yeah. So it's providing some kind of explainability for the process and for what happened exactly in order to make the final decision. I think the one of the questions that here, like on the Q&A, like it's also related to maybe the second part of my question, which is the question says here, like by human insight, do you mean for data preparation, like the data preparation part? Do you mean data scientist or end user? So yeah,
good question. I mean the domain knowledge, the person with the domain knowledge, the domain expert. So like one thing that we've discovered is that, for example, one of the common practices even in production companies is that if you have a large number of features, you ask the domain expert to prioritize them. Because combining features can be easier if the domain expert can weigh in on which are the more important ones. Sometimes that's a data scientist, sometimes it's the product manager, sometimes it's the end user, but you're looking for someone with insight to the problem. That's what human insight.
Yeah, but this is also like difficult for like non-technical users, right? Because data scientists have also a feeling of the data itself. So leaving it just for the machine to decide, do we reach really good, or do we really, the system that will be produced will be good enough in this case?
No, it's a really good question. So I can tell you that, for example, I think what at least my experience has been that the full complete automation without human is not going to result in the best effectiveness. Usually simple human insights can just go a tremendously long way towards simplifying the problem for automation. That's at least my personal opinion on it.
So we have another question about, I think, portability and interoperability, especially that you talked about different cloud systems and this pipeline that you defined over cloud systems. So in this regard, like it's like the question says, like regarding end-to-end automation, are the efforts to standardize the ML workflow format across cloud ML? Are there efforts for standardized format across cloud ML platforms? And to ensure like interoperability and virtualization, etc. So is there like efforts in this regard?
I am not aware of any. I'm not aware of any. It's also likely that right now it's really not in the economic interest of any of the cloud vendors to do that. They're mostly trying to draw people into their platform. So interoperability with their other tools is a higher priority than them.
Well, from my own experience, I noticed also I worked in the field of model-driven engineering and trying to be able to create this kind of agnostic platforms. There's lots also of challenges in adoption because the platforms itself evolve over time, and this makes this kind of uniform kind of pipeline obsolete with time, or it requires really lots of effort to keep it up to date when the technology changes.
I totally agree. And I think that's one of the reasons why I would not expect standardization in this area anytime soon. Yeah. It mostly just,
so we have one last question. It's about the AutoML. So one issue with heavily relying on AutoML and code generation might be that application developers have to completely trust this automation. Do you ever encounter any issues with this, for example, with businesses or safety critical applications? And would you recommend such an approach in such scenarios?
So I think that code generation and automation is really mostly useful as a starting point. And it isn't, so the idea of code generation, particularly in my view, is not about trying to get completely functional code that you should put into production. It's about getting a starting point that you can improve upon. So I think for those kinds of use cases, absolutely. I think a human eye and, massive testing is required. I personally wouldn't use the automation as anything other than where to begin. It's either begin with a blank window or begin with that. Just saves you a bunch of work.
Okay, so I think we're reaching a point where we're over time a little bit, so we can conclude today's talk and this interesting talk and session. Thank you very much for your time and for this great presentation. I think on behalf of the SEMLA community, we thank you and all the audience here that's online.
Thank you very much. I really appreciate it.
Thank you. Thank you very much, Nisha. Great, insightful talk.
Thank you.
Really enjoy.
Take care.
So,
Thank you.